Alright, so with the trisection, using the insertion principle, the question is, why does this work? And if you think back to the image we had, I have added one additional segment that is within the image, it's just not visually there, which is DF. But what we know, and we're assuming this to be true because of how we constructed it, we know that EF and GF are congruent because those were radii of the circle. DF will also be congruent because it is actually going to be a radius of the circle. And if you look back, you would see that when it intersected and went through G, it also went through D. And this is all built off the insertion of AD. And we want to show why is BAD 3 times that of BAG. So the easiest way to think about what's going on here is to look at what relationships I do have. So this is a rectangle, so I'm going to state that ABCD is a rectangle. What that tells me is that line CD, I want to say line CE is parallel to, I'm going to just put segment AB. Then what we know, I'm going to mark it here, is that BAG is congruent to FED. So the measure of angle BAG is equal to the measure of angle FED by alternate interior angles of parallel lines. And I'm using a lot of abbreviation to try to save some space. So I have these alternate interior angles. What else do I know? Well, I also know that if I look, I have multiple isosceles triangles. I'm going to erase one that, I'm going to take this out of the way just to get out of the way for a second. So if I look, I can see that these two angles, GAD and DFA, are going to be congruent because triangle ADF is an isosceles triangle. So I'm going to say since triangle ADF is isosceles, the measure of angle FAD equals the measure of angle AFD. AFD, yeah. Okay, we're getting close. Now, one last relationship puts all of this back together. So that other relationship is that I have one other isosceles triangle up at the top here. Oop, sorry. And here I'm going to just undo, there we go. I'm going to use a different color, but what I know is that these two angles are also congruent. So the purple and the red are actually congruent. So if I want to, because it's an isosceles triangle, I could just put in here another red and say that since triangle EDF is isosceles, the measure of angle DEF equals the measure of angle FDE. And I'm going to use one last relationship to help me, and then I'll have it to get these parts together. And that last relationship is recognizing that I have the exterior angle of a triangle, and I know that that's equal to the sum of the remote interior angles. So I can say since angle AFD is an exterior angle, of triangle FDE, the measure of angle AFD is equal to 2 times the measure of angle FED. Now, I made a jump there, but the jump is okay because I know that it's FDE plus FED, those two angles here, but they're the same, so I can just say that's 2 of FED. Why does that become important? Well, remember at the beginning that we said that BAG is equal to FED. So I'm bringing that back now. So by substitution, the measure of angle AFD equals 2 times the measure of angle BAG. Thus, also using substitution, I can say that the measure of angle FAD is equal to 2 times the measure of angle BAG. So now what we find, if you follow what just happened there, is that this angle is 2 times this angle. And if we think about 2 times plus 1 times, that means that that BAD has to be 3 times that of BAG. So by showing that that angle is double BAG, I can now put my triple marks there, and therefore the measure of angle BAD is 3 times that of the measure of angle BAG. So because that one angle is twice as big as BAG, that means the larger overall angle is 3 times as big. It's kind of a unique relationship that is always true. And that's how you show that why the insertion principle is an appropriate method, other than the fact that it does not follow the classical tools.